Gary Shiu. Gary, could you share your screen, please?
Do you see it in full screen mode?
Yes.
All right, so thank you very much for having me here. In this talk, I would like to present our initial forays into the string genome project, and it should become clear what this title means. So this talk is based on joint work with my wonderful collaborators, Alex Koh, Andres Schackner, Sven Krippendorf, and Gregory Loges in different combinations. The first two papers have already appeared. The third will come out in a few hours on the archive near you. So the overarching theme of our work is to address the age-old question: is excellence the result of nature or nurture? Now, just to be clear, our work should not be construed in any way as support for eugenics. Quite the contrary, we show that genetics and training are complementary. Both lead to Rome, but through different paths. And as a result, different traits are uncovered. So having one but not the other could miss some important blind spots. Now, the question of nature versus nurture is particularly relevant for string data. The landscape is vast, making exhaustive searches or random sampling impractical. So the question that we would like to address is whether genetic-based optimization methods or reinforcement learning can effectively search for desirable string vacuum. Now, desirable could mean different things depending on the questions that you want to solve. But more importantly, we want to know whether these methods can discover structures on the landscape. And if so, are the structures discovered by genetic methods the same as what one finds by training? So in a series of work, we show that genetic algorithms and reinforcement learning are both effective in finding desirable string vacuum. We demonstrate that in two different contexts. In finding flux vacuum with a specific range of flux superpotential and string coupling, and in finding intersecting brain models that give realistic particle spectrum. Now, this works. We further show that these methods can uncover structure in the landscape, but in complementary ways. So let me say a few words about genetic algorithms and their relevance for the landscape. Now, taking inspiration from nature, genetic algorithms solve or find optimal solutions by mimicking biological evolution. So a population of individuals becomes fitter as selection, crossover, and mutation improves their offspring over time. Now, many landscape problems take the form of an inverse problem with discrete variables. For example, we want to know what fluxes gives an optimal value of the cosmological constant, or what kinds of brain configurations would give a realistic particle spectrum. So traditional gradient descent methods are not directly applicable because of the discreteness of the variables involved. Genetic algorithms provide a powerful alternative to solve these optimization problems. So the problem of finding string vacuum with energies within a specific range falls in the same universality class as the knapsack problem. So we could take this simple example to illustrate how genetic algorithms work. So suppose you were given a collection of items with certain weights and values. Your task is to find the subset which maximizes the total value without exceeding the capacity. Now, what is shown here is a knapsack problem with only 5 items, which you can easily solve by brute force, but let's see how genetic algorithm does it. So an individual in the population consists of a chromosome, which describes a choice of items. Okay, so this chromosome can be represented in a binary way, with one meaning that an item is selected. So for this individual, these 3 items have been selected to put into the knapsack. So the fitness function, which measures how well the problem is solved, is something that we want to maximize. For instance, the first choice of items exceeds the capacity. So this solution is terrible, and the fitness of this individual is 0. This other choice of items is still within the capacity, but there's plenty of space left. So this is still not yet the optimal solution. The last individual shown here is, in fact, the optimal solution for this problem. The knapsack contains the maximum value within the capacity. So it has maximum fitness. So the way genetic algorithms find this optimal solution is through selection, crossover, and mutations. We first select fitter individuals within the populations to breed. This can be done by a number of binary tournaments. Then we combine the chromosomes of the parents to create a child. This can be done by a one-point crossover, like what is shown in the 2 examples here. You chop the chromosome at one random point, and you splice the chromosome together to produce a child. But you can also consider crossover at multiple points. Now, mutations ensure that the new generation is sufficiently diverse. You can, in this problem, flip each bit of the chromosome with a probability p. Too low a mutation rate does not improve diversity, whereas too high a mutation rate does not lead to convergence to an optimal solution. So there is some hyperparameter tuning to do here. And the efficiency of genetic algorithms can be seen from a slightly scaled up version of this problem. Suppose you have 16 rather than 5 objects. You can reach an optimal solution after the order of 10 generations for a population size of 50 and roughly around a few hundred unique states visits. This is in contrast to a lot more states that you need to sample with a brute force approach. So back to the landscape. The data structure of string theory is often characterized by a set of integer inputs. For example, in flux compactifications, these integer inputs are the flux quanta subject to tadpole constraints. And if you're considering Calabi-Yau compactifications, the input vectors could be a set of topological invariants. The output is often a vector of complex value fields, which minimizes a potential or an energy function. Physical observables are then computed from this output. And what we want to solve is an inverse problem. We want to know how to identify and characterize the input vectors, integer input vectors, that leads to particular physical properties. But the challenge for string theory is that there are a lot more vectors in the landscape than items in a knapsack, but very few of them are phenomenologically interesting. So we are facing a problem of finding a needle in a haystack. So in our recent NeuroRips paper, we use 2 different optimization methods. One is genetic-based, and the other is learning-based, to find desirable vector and compare them. So earlier, our team and Sven's have separately applied genetic algorithms and reinforcement learning on the same set of flux vector. And so we decided to join force to compare and contrast these methods. Our joint work is the first comparison between genetic algorithms and reinforcement learning in the string theory context. Now, to improve efficiency, we optimize the reward structure for reinforcement learning. And on the genetic algorithm side, we optimize the hyperparameters by computing correlations with the mean average distance to the optimal solutions. So by looking under the hood, we can understand how each algorithm finds optimal solutions, as well as discover local structures of the landscape. To gain insight, it is advantageous to start with as simple a model as possible. For instance, we don't want to start with flux compactifications with hundreds of moduli. So for that, we consider a one-parameter family of Calabi-Yau manifolds defined by a hypersurface in complex projective space. Since there's only one complex structure moduli, there are only 8 fluxes. So our task here, the optimization that we need to do here, is to find the set of flux vector that gives a superpotential within a specific range. And since we are doing it for illustrative purpose, we set our target value of the flux superpotential to be 50,000, which ensures that many flux vectors can be identified within reasonable effort. Okay, so to discover structures on the landscape, we perform a principal component analysis on the 8-dimensional flux space. And from the PC8, we identify or we observe 2 clusters. And this is a universal feature common to both genetic algorithms and reinforcement learning. And we find this quite remarkable as the sampling dynamics are very different in these 2 approaches. Okay. But the 2 methods do not learn to find vacuum in the same way. The scaling with respect to one of the 8 fluxes that we call N1 reveals distinguishing features between genetic algorithms and reinforcement learning. As we increase this flux N1, in genetic algorithm, we go from one cluster to the other, whereas for reinforcement learning, we stay within the same cluster. The existence of these 2 clusters also hinted at a discrete C2 symmetry, which you can see here maps one of the fluxes to its negative value. Furthermore, the low variance of the higher principal PCA components, which are not shown here, suggests that the flux distribution, even though the space is 8-dimensional, is effectively lower dimensional. Not only that, correlations of the flux vectors reveal further structure. Okay, so combining samples from genetic algorithms and reinforcement learning allows us, before we compute the correlations, which is what's shown on the left figure here, allows us to reduce sampling bias. Okay, so the combined correlation map shows strong correlations, which are also shared by the individual correlation maps, but the converse is not true. So some of these correlations can be easily understood. For example, pairs of fluxes contribute as products to the tadpoles. And so these fluxes are correlated or anti-correlated. But there are also correlations among the fluxes that we find that cannot be explained in this manner. Moreover, by comparing the individual correlation maps with the combined one, we can unpack how each algorithm finds its solutions. So the takeaway of this work is that genetic algorithms and reinforcement learning are both efficient in finding desirable string vacuum. Combining them allows us to identify universal structure in the landscape with reduced sampling bias. The kind of universal structure that I refer to here include the presence of the 2 clusters, the presence of a discrete C2 symmetry, and the correlations of the fluxes. These algorithms, especially when used together, can uncover symmetries and correlations on the landscape. The natural next step is, of course, to go from this very simple example to more challenging situations and to optimize other phenomenological features. And this naturally brings me to the upcoming paper with my graduate student, Gregory Logis, on breeding realistic deep brain models. Now, the problem that we want to solve is, again, an inverse problem. We want to know what discrete choices, namely what are the number of brains, how they wrap on the internal space, would give realistic particle spectra and couplings. So the concrete setup in which we breed models is type 2A orientifals with intersecting D6 brains. And the reason for choosing this environment is that a number of desirable phenomenological features such as non-abelian gauge groups, replica families of chiral matters are already built in. Now, to learn how genetic algorithm finds optimal solution, it is again useful to start with the simplest example. The harmonic oscillator in this context is a Z2 cross Z2 orientable. This is the setting in which the consistency conditions for four-dimensional n equals to 1 models were fully developed, and three-family standard-like models were first constructed. Subsequent work on landscape statistics, proof of finiteness, and reinforcement learning were all done within the same setup. I mention this because this subject has become somewhat of a cancel culture. Recent practitioners of string data were not aware of how this framework was developed in the first place. And this is ironic because with the exponential increase in computing power and advances in AI, computer searchers still cannot beat humans, which are products of nature's genetic algorithm. So the purpose of our upcoming work is to come full circle and see how human-made genetic algorithms fare with nature's genetic algorithm. So these orientable models are also interesting from a duality standpoint. They are weak coupling duals of G2 compactifications of M theory. And because of the Z2 involutions of the orientable, only two discrete choices of torus shapes are compatible with this symmetry. So one of them is the rectangular torus, and the other is a particularly tilted torus. And we will label these two discrete choices as B equal to 0 and B equals to 1/2, respectively. So the D6 branes we consider are space filling and wrap on internal 3 cycles. They intersect at a point in the internal space where the chiral matter is located. For them to be supersymmetric, the 3 cycles are special Lagrangian. Now, in this toroidal orientable model, we can consider a special subset where the 3 cycles are factorized. Namely, they are products of 1 cycle on each T2. This is a relatively easy subset of 3 cycles to consider in this setup. And these factorized 3 cycles are specified by 3 pairs of coprime integers. So we could, in general, expand the 3 cycles on which the 6 brane wrap in the basis of orientable even and orientable odd cycles. So instead of working with this individual 1 cycles on each tori, we would like to work with a basis in which the 3 cycles are already known to be odd or even under the orientable symmetries. The coefficient of this expansion, denoted by x and y here, take integer values. So they are vectors with integer value components. Now, the consistency conditions that these deep brain models need to satisfy include temporal cancellation, which is nothing but Gauss's law, K-theory constraints, which ensure that the model is free of global anomalies. And for the model to be supersymmetric, if we are considering supersymmetric models, that the 3 cycles are special Lagrangian. Now, the fitness function should measure how well these conditions are met. A bottleneck in previous computer searches is that the supersymmetry conditions depends on this moduli, which takes real values. So there's no straightforward way to do a complete computer scan. But in our upcoming paper, using matrix algebra, we prove a little lemma, which allows us to, without loss of generality, to take this moduli to be positive coprime integers. Now, this lemma is very useful and can greatly simplify the search for consistent models. Now, in proving the finiteness of the number of supersymmetric D-brane models, it proves useful to classify the supersymmetric branes into different types according to how many components of the integer vectors are positive, negative, or 0, and this was done in the paper by Douglas and Taylor. One of these brains, known as the C-type brains, are what we call filler brains. They are special in the sense that they preserve supersymmetry for all choices of complex structure moduli. They satisfy the K-theory constraint automatically, and they only contribute positively to only one of the tadpoles. In fact, the proof of finiteness is non-trivial because even though these brains are supersymmetric, they could contribute negatively to some of the tadpoles, even though overall the contributions is still positive. And for completeness, we classify also the non-SUSY brains, which are denoted by prime here. They can never be made supersymmetric, but they can be generated in the genetic evolution. So the number of brains and how they wrap on the internal space determines the gauge group and the chiral spectrum, as well as other phenomenology. The fitness function should also measure how close is the spectrum to the standard model. So we are now ready to breed deep brain models. So let's start with the environment. What defines an individual? The chromosome of an individual consists of the number of brains in each stacks and the winding numbers, which are pairwise co-prime. If there are k stacks of brains in this construction, the chromosome is 4k dimensional. The size of the chromosome is 4k dimensional, but not every members of the populations have chromosome of the same size. They could have different set of brains. Now, the genetic algorithm operates in an environment where the moduli are fixed. You could consider different types of search environments. You could consider environments where all brains are allowed, supersymmetric or not. You could also consider environment with a reduced search space. For example, you could eliminate any non-supersymmetric brains by mapping them to the supersymmetric ones. Or you could remove the filler brains from the chromosome and just add them later to maximize fitness. And we have tried to run our genetic algorithm in these 3 different environments. Now, as for breeding is concerned, we employ 8 crossover methods. These crossover methods differ in several aspects. The number of crossover points, which can be either 1 or 2, where the crossovers are located, whether this is between stacks of brains or between genes. And finally, you could demand that the size of the chromosome of the child to match with one of the parents. This is not guaranteed. As I said earlier, different individuals of the populations can have chromosome of different size. And the third types of crossover methods could restrict the size of the chromosome of the child to match with at least one of the parents. Okay, so unconstrained here means that we don't make that restriction, but the constrained ones are those where the size of the chromosome of the descendants match with that with one of the parents. Now, mutations keep the population diverse. There are several mutations we could do. We can change the stack size by 1. We can change the winding numbers by 1 or 2. 2 here is useful in some cases to make sure that the winding numbers are relatively co-prime. We can also randomize the signs of the genes, or we can permute the genes in a chromosome. These are the kind of mutations that we could do. And the fitness functions measure how close an individual is to an optimal solution. And this includes how close are the tadpole conditions, the K-theory constraints, the supersymmetry conditions get satisfied, as well as the distance to the standard model. Okay. Each of these fitness functions come with a weight. We have done hyperparameter tuning with these weights to optimize performance. But there's one crucial last step before an individual can be added back to the population. This is because crossover and mutations may lead to a chromosome that lies outside the scope of the environment. And so that's the reason why we include an adjustment phase. And the adjustment phase is implemented in a stochastic manner to ensure diversity. There are many ways to adjust the chromosomes to make it part of the environment, and we do it in a stochastic manner so that the individual that is put back into the populations is not, following some specific patterns. Now, our genetic algorithm has around a dozen parameters. Some of these parameters are environmental. They define the environment in which we conduct our runs, like the shape of the torus, the values of the moduli, and the maximum number of brains, for instance. But there are also meta and hyperparameters. For instance, the number of the size of the populations, the number of generations, the probability of having certain crossover, the probability of mutations, the weights, and so on. These hyperparameters and metaparameters are tuned to optimize efficiencies. So we can now go under the hood and understand how genetic algorithm learns to find optimal solutions. For this purpose, we can temporarily switch off the fitness function, which measures the distance to the MSSM or to the standard model. And this is a single run for a population size of 250 and over 100 generations. So you can see, starting from a terrible population, I forgot to mention that our fitness functions is normalized in such a way that fitness function equals to 1 means the most terrible. They are normalized in such a way that 0 is the best. 1 is terrible, okay? Most terrible. Starting from a terrible initial population, we start getting fully consistent models after about 50 generations. We can also see how genetic algorithm learns to find solutions. It learns to first solve the supersymmetry conditions before adding in fewer brains to cancel the tadpoles. Okay. And this point can also be exemplified by the figure on the top right. You can see how many brains of each type appear as we run through the generations. You see that the supersymmetric brains A, B, and C are the ones that are most popular, most dominant. And after 50 generations or so, the filler brains begins to proliferate. This is when you move from here to satisfying the tadpole conditions. And you can see that a sizable fractions of the populations are fully consistent around 80 generations or so. Now, our genetic algorithms can easily generate 1 million consistent models in a few hours. With a sizable sample, we can begin to draw landscape statistics. We can ask, what is the probability of finding a gauge group with a certain rank? This is shown in the picture on the left. We also find evidence that the probability of finding an SU2 and an SU3 gauge factor to be roughly statistical independent. We can only do that with a sizable sample. And we also find that as we have more and more tori that are tilted, this B denotes how many of them are rectangular and how many of them are tilted. As more and more tori are tilted, the rank of the gauge group peaks at smaller values, and furthermore, the odd rank gauge group are less penalized. This confirms a humanly discovered strategy more than 20 years ago. Our landscape statistics also show anti-correlations between the mean chirality and rank. For other correlations and landscape statistics, I will refer you to the paper that will come out later today. So in summary, we have demonstrated how genetic algorithm and reinforcement learning can efficiently find desirable string vacuum, desirable in different ways. More importantly, these methods can be used to discover structures on the landscape. And then the structure that is discovered also are complementary. The methods do not always discover the same thing. And this resonates with the structures that we find in an earlier work using topological data analysis. Our studies highlights the similarity and differences of the strategy use. I have presented some preliminary landscape statistics. More can be found in our upcoming paper. And I hope I have conveyed to you the message that genetic algorithms and reinforcement learning are complementary. Together, they may lead us to the elusive string vacuum in which we live. Let me stop there. Thank you for your attention.
Thank you very much, Gary, for excellent talk. It has been a great session of talks today. Now we have about 1 hour for any questions from Gary or any other speaker of today, or anyone in the audience who would like to join discussion. Fabian, please.
Hey, Gary, thank you very much for the nice talk. Can I ask a question about the first part of your talk where you showed the distribution and the clusters that are learned by the genetic algorithm and the reinforcement learning?
Yeah.
Yeah, I'll wait until you pull it up. It will be easier to explain what my question is.
I think this is the food.
Yeah, yes, thank you very much. So you can see these sort of diagonal lines in the genetic algorithm, and the reinforcement learning looks more like a more more uniform point cloud. Are these lines an artifact of a small mutation rate? Did you check whether if you make the mutation rate larger, this becomes like a more uniform point cloud?
You are talking about whether here it doesn't look as fill up and uniform as the reinforcement learning shows. Is that right?
Exactly. So there are these differences. These sort of you see this diagonal line pattern in there, and I was wondering whether this is sort of the imprint of having the mutation and the smaller mutation rate into the GAs, sorry, in the principal component, and whether this goes away if you make your mutation rate larger. Do you know?
Yeah, so here we are comparing the best scenario on both. We optimize both reinforcement learning's reward structure and optimize the hyperparameters for genetic algorithm. You may ask, if you don't optimize, how do they compare? I don't know. So, I mean, we already used the optimized hyperparameters to compute this, to show you this PCA.
Okay, so you didn't.
So here, I'm not choosing one particular hyperparameters and show it to you. I consider a bunch of hyperparameters and find the best case to show you the results.
Yeah, I was just wondering whether whether this imprint that you see there is related to the hyperparameters at all, or whether it's something more intrinsic to the algorithm.
Maybe I can jump in. So I certainly agree that this is, of course, related to the choice of hyperparameters. I would have expected it to be rather related to the crossover rather than to the mutation. But yeah, no, we haven't tested it in the sense that you just mentioned. So no, we haven't looked at if you take another choice, if it looks more randomized. No, we haven't done that.
Okay, thank you.
Okay, Anindita, you may unmute yourself.
Thanks. My question is more on the data science side, using the comparative performance of reinforcement learning and genetic algorithms. Can you make predictions on what kind of optimization problems are better suited for genetic algorithms versus which ones are better for reinforcement learning?
So I think if we could, we should do both. I think the main theme of the talk and from all the work is we should try to use all possible ways, and especially combining them before drawing statistics or correlations, because they could reduce sampling bias. Right? So there are blind spots. I mean, if you look at the PCA, you saw that some regions are not discovered by one of the learning algorithms. So combining them, I think, would be the way to go. And as far as comparisons of general, performance, I don't think there's a uniform answer. It's highly depending on what problems you want to solve. Some of the problems are identical. Some of them are not. So, for instance, referring to the second part of the talk where we look at intersecting brains, the bottleneck for most of the reinforcement learning effort to search for solutions is that some of these conditions are not easy to scan. They take real value instead of integer value. And the kind of matrix algebra lemma that we prove can be directly implemented into reinforcement learning. And I bet the performance would be hugely improved because of that.
Thank you. That makes sense. I have a second small question, which was actually answered. Should I ask that now or should I wait for the discussion?
Up to you.
Thank you. I'll just put it forward. Is there any theoretical obstruction to combine the factors from reinforcement learning and genetic algorithms that those are contributing to better search and combine them together to make a more appropriate optimization technique that works for string landscape? Is there any, from the physics side, are there any obstructions that do not let us do that?
So certainly you can use genetic algorithms to optimize your network. I mean, that's a cheap answer because genetic algorithm not only finds optimal solutions, they could also find your optimal algorithm. So you can use GA to find what is the reward structure that best find solutions. Maybe Andres have thought more about this.
I still struggle to understand the question. You mean, is there an obstruction to apply both methods in a combined way? Is that what you're asking? Right,
like come up with a more hybrid optimization, a search problem.
No, I wouldn't say that there is any obstruction. I think since we, in a sense, joined two different collaborations, the first thing to do was to compare the algorithms separately. But yes, I agree that ultimately what we should try to achieve is to combine the two or even different approaches to optimization, because in the end, there are so many different methods to choose from that, and that's also something that we highlight in this paper. It is beneficial to use several optimization strategies because thereby you also reduce the bias of the individual search algorithm itself. So I think in the long run, we should aim for that, but so far we haven't done it. Yeah.
So one other comment is you can possibly put in some of the nice features of genetic algorithms into your reinforcement learning with some mutations. Mm-hmm. I mean, so the way reinforcement learning solve problems is you have a fixed, set of steps to follow. You increase the flux by 1, you change the, there are very well-defined steps that the agent would have to follow. But if you include some stochasticity there, you could possibly, improve the diversity of the solution, which is why genetic algorithm works quite well in many cases. I could think of many combinations, but maybe not everything we want to do could be done in one, umbrella algorithm.
That makes sense. Thank you so much.
Yeah, thank you. David.
Hi, Gary. Just this is maybe quite a general question about genetic algorithms. So maybe it's more for the discussion, but anyway, I'll ask. So when you're picking the mutation rate as a hyperparameter, you had this conflict between convergence and having enough mutation to explore difference or whatever. And I was just curious because I came across a thing recently that actually in nature, the mutation rate can often be dependent on the population size. Mm-hmm. So this is something that is in reality and is an important part of human genetics. That there are different mutation rates that have happened at different points in human history. Mm-hmm. I was wondering if people look at stuff like that, or whether that's just a freak of what happens in real nature, or whether that's actually gives us an advantage in a search.
There's actually a rule of thumb on how big is the mutation rate you need to choose. And I learned it from Gregory. He could probably say it better than me. I think if you have a population size of, I don't know, n, then you want at least one of the members of the populations to be mutated. So that basically tells you that it's 1 over p, but 1 over n. But Gregory could make a more clear statement about it.
Yeah, so that's almost right. It's that for each individual, you should expect on average 1 mutation be applied. and then this will happen to each individual in the population.
Does it matter how harshly you penalize the population? So you've got something of fitness in the sense that if you're close to fitness versus being far away, you could imagine it would then get a different tuning that you might want rather than just the size. Because again, this is also what happened in humanity. There's a thing called the great bottleneck where there was a lot of harsh things going on. There was floods, famine, God knows what, probably a pandemic. And the mutation rate at that point changed, you know.
Yes.
And I'm curious whether that sort of thing also could play a part.
Yeah, so here the mutation rates are fixed throughout the evolution from generation 1 to generation 100. You could imagine that there's a nuclear explosion somewhere happening in the middle, and you have to change your mutation rate.
Yeah.
So you could make this also an added complexity to your model to have varying mutation rates to adjust to the situations, like in humanity's example that you mentioned.
It's a general thing. It's just because I came across this thing recently and
Right.
I thought it was curious how it might apply to genetic algorithms. But anyway, thank you very much. Thanks.
Yeah, thank you.